I am Steve Oakley from American Airlines, and we're honored to be able to share today about our simulation approach for aircraft spare engines and engine parts planning. I'm going to go through some background about who we are and what we do, and then introduce the problem. So today we're going to talk about spare engines and engine part spares, or what we call shop pool. And while, don't worry, if you're not interested in engines, this type of work, both on our theory side and our application in the simulation, can be applied to any kind of repairable part. So it could be in the industry of construction or manufacturing or mining or transport services, not just the transportation or airline industry. Okay, Jose will pick it up there and go through our approach and talk about case studies. Application of what we've done and how it affects AA, and then we'll wrap up with conclusions, and then there will be that time for questions and answers. Okay, we are American Airlines, and after our merger with US Airways in late 2013, we are now once again the largest airline in the world, as measured by revenue passenger miles. We have over 1,000 aircraft. We carry more than 500,000 bags a day for more than 300,000 passengers, and that takes a large employee base of about 100,000 people. Within that group, there's a much smaller group of focused operations research and advanced analytics professionals. And we do internal consulting and decision support for major business units. So Tech Ops is maintenance and engineering, just another name for that. Revenue management, which would be overbooking, seat inventory control, and controlling the fares and such. Network planning, or the schedule and crewing and things like that, and many other business units. We can do consulting for any business unit in the airline. Here's a picture of the group. We have 36 people from every inhabited continent on the world, speaking 20 languages, hailing from 12 countries, and having a multitude of advanced degrees in OR, patents, journal articles. Okay, maintenance operations. Now, in an airline, one of the most expensive items is maintenance. The top three typically would be wages and salaries, jet fuel, and maintenance. So it's very important. It's critical to the operation in a couple of ways. We want to have reliable aircraft, and we want to use them efficiently. So we need to have maintenance to support that. And American does a lot of its own work, so we have maintenance bases. Our biggest one is in Tulsa, Oklahoma, but we also do work in Charlotte from our merger, and in Dallas itself, where our headquarters is. At those bases, different types of work gets done. So engines like we're talking about today, landing gear, avionics, electronics, lots of things at the small scale, but also all the way up to a full aircraft overhaul. And that's when we basically tear a whole aircraft apart and rebuild it. Right? That's a huge operation. On the OR side, we support inventory and supply chain, so anything having to do with parts, we were involved with that. Line maintenance, so that would be maintenance operations out at the airports, and aircraft overhaul, like I mentioned, and reliability and asset planning, and that's where the engines come in. Right? Engines are a major asset for the airline, and they're expensive. Right? If you own your own engines, you have to make a major investment, and once you own the engines, you have to have that supporting inventory to deal with repairs. Now, if we can use analytics and do good planning, then we can realize some significant savings. It's important to point out that in the airline business, analytics is accepted in areas like revenue management and scheduling or crewing. But in the maintenance world, analytics is not so accepted. And this work represents a major step for us forward in really getting a footprint of showing what analytics can do to the bottom line. Okay, spare engines are critical in two ways. One is operationally. So I mentioned a full aircraft overhaul. Engines also need to undergo these overhauls. So this is an operation that might take several weeks and cost in the single-digit millions of dollars. And while the engines are undergoing that process, we need to have spare engines to be able to cover it. So we got to meet our flying schedule. We're going to have complete spare engines. On the financial side, let's look at some numbers. So for a mature fleet like our Super 80s, the market price might be about $1 million. For a newer fleet like our 737s, more like $13 million. And finally, for our wide bodies, It's a large aircraft and a large price tag, $35 million. That's for a single engine. For our 737 fleet alone, which is our largest sub-fleet, has about 250 planes and still growing as we get new deliveries. The investment is $180 million in spare engines. Okay, let's move on to engine parts planning. You can see from the picture of the engine here, an engine is a complex piece of machinery. It's got over 800 parts in there, and it's difficult to deal with that at times when it undergoes a repair. There are lots of factors that introduce uncertainty and variability. Some of those might be scrapping. A part comes off an engine, and maybe it's run out of time, maybe it's for some other reason it's not usable, we have to throw that out. We might borrow a part. If we don't have a part in inventory, we can look to an upline engine. Maybe we can borrow a good part from another engine and save ourselves the effort of buying one. And finally, engine harvesting. That's more of a rare event, but we need to model it when we might be retiring a fleet. So we have an engine parked out in the desert somewhere, or a plane parked out there, and there are engines on it, and we can use those engines. So that can help us delay some of our maintenance costs. We want to do accurate planning for our shop pool, or this inventory of parts, because it can help us reduce the amount of time it takes to repair an engine and the variability associated with that, and also reduce the number of whole spare engines that we need to keep. Now, I talked about some of the expenses of the engines themselves. The spare parts also cost a lot of money. We have in the neighborhood of $70 million of investment in our shop pool. Okay, spare engines. This process is fairly straightforward. But let's take a look. When an airplane comes in, if the engine has to come off the wing, we take it out and we send it out for repair. So it would be sent to, say, Tulsa for the shop work. Now, ideally, we would have a spare available there. But let's say that it's not there for whatever reason. If it's not there, the aircraft can't fly. And we say it's out of service. So keep this in mind, because we're going to be talking about this later as a measure of how the system operates. It's unavailable to fly. We have to wait for a spare to come before we can do anything with it. That affects our revenue. And for the passengers, you can see the dreaded delay or cancel on the airport monitors. Nobody's happy, right? Let's look at another angle on that, all right? Now, if we do have the spare, then we go through the same process, right? We take it off, we send it to the shop. But we have a spare up there, and it's important to note we want to have the right number of spares, right? If you need 2 spares somewhere and you have 4, that's a waste of our money. We don't really need to be investing that money there. We need to put those spares somewhere else. So financially, we do not want to overstock. Okay, so if we have the spare, we can replace that on the aircraft. Everything's good. Our bottom line should be okay. And instead of those delays, we should see more on-time flights, right? And we're all happy, customers and employees alike. Okay. Let's move on to the engine removal, disassembling, and piece part repair. Before we go into the details, we'll do a little pictorial view here. This is an on-wing engine up close. These things are massive pieces of machinery. We looked at how sophisticated they were with the picture of the inside. They're also big. If you look at a wide-body aircraft, you can see it dwarfs these 5 guys, right? And it takes special equipment just to be able to handle these. We have that equipment in Tulsa. I mentioned our base. Here it is. At Tulsa, we can do major repairs on narrow body and wide body. We have hangars there for that. We have an automated parts warehouse to support that operation, as well as the administrative offices. Okay, here's what an airplane looks like if the engines have been removed. You won't see that too often, and neither do I, actually. And here's the engine itself in the shop. So they come in and they're on racks, and they move through the various stages of the repair process. And there are a lot of other elements as well. Parts that go in the engines, blades, vanes, different components that we need to worry about as far as our inventory. Okay, engine repair programs are divided at American into 2 types. There's light repairs and heavy repairs. A light repair would be something similar to getting your oil changed, right? Engines also need oil. They need routine type maintenance. We can do that fairly quickly. We're not really going to focus on those today. We're going to look at the heavy repairs. I mentioned earlier that we can harvest engines. Just keep that in the back of your mind. It's again, a rare case. But on the heavy repairs. So we're talking about an engine going through this weeks-long repair overhaul process. It's very expensive, but engines are durable. today's modern engines can go years without having to do a heavy overhaul. So that's good. They can take a lot of wear and tear. You can go up to 15 years between major work. Now, in that process, there are issues that we need to worry about. So the shop has a capacity. There are only so many racks, and there are only so many skilled workers. The labor force is limited, so we need to worry about that. And I mentioned the scrapping and borrowing. We'll look into that in a little more detail. How does the engine repair process work? Well, at the 32,000 foot level for our business, there's 6 basic steps. All right, we introduce the engine into the shop. That's the arrival, and then we take it apart. So out of the 800 components in the engine, we might take out a majority of them, and then they're shipped out for what we call piece part repair. And we'll be focusing on that process today. Then at some point later, we want to reassemble the engine, put everything back together, test it, make sure everything's working properly, and then we can ship it out and put it in the right spot for a spare engine inventory. Okay, that's the broad view. Let's look at a more detailed version of that. So in the shop, they'll have something more akin to this. And this is the same map as up here, it's just more detailed. Okay, so we have up here disassembly. Well, down here in submodule removal, major removal, that corresponds to disassembly. Engine test is this little slice over here, reassemblies here. We're going to focus in on piece part repair. So this red arrow here is our turnaround time target. This green arrow is when the parts are sent out. So the parts are sent out for repair, in this case at day 9, and that might be to an external vendor, so we use outsourcing, and it might be to an internal shop. We have several AA shops that work parts. And then later on at day 34, we want to be ready to put the engine back together again. Now, we're going to take a very detailed look at that. This is a timeline, and you see our red arrow of our turnaround time target, and turnaround time is exactly that. It's time to turn around getting the parts back from when we send them out. Okay? So we have a turnaround time target. On the left side is going to be when we send these parts out for repair. Okay? So we have here some blades. They might have various times of repair. In that process, we do lots of things. So parts need to be inspected. Parts might need to be cleaned. They might need to be lubricated, polished, buffed. Maybe some more severe work, milling and grinding. So there's a lot of variability here. You might have some short ones. Oops, skip ahead a little bit there. Or some longer ones. I mentioned earlier that we have some scrapping. So here, by these red X's, we denote scrap parts. Those we must replace. We have to purchase a new part. So we'll put through a purchase order and get some new parts to replace those scrapping. And that scrapping could happen early in the process, or it might happen later. You might start working a part and accidentally do something and have to scrap it. So more variability. Okay, now check this out. We're at this turnaround time target. We want to start reassembling the engine. But there may be some parts that have not come back from the shop yet. We're not able to do that. We're not able to use that same part. That's what shop pool is for. Shop pool is inventory that we can use and pull out from to put the engine back together. Now, it may be that we don't have a part in shop pool. If we run out there, there's another option. We said we may be able to borrow a part. So if we go upstream a bit, find an engine that hasn't been introduced into the shop, then we can use a part from there. Ideally, everything's ready to go. We use parts from shop pool or from borrowing. We put the engine back together again. We test it, and we ship it out. Now, Jose's going to clarify exactly what we want to do from here and our objective and how we went about doing that.
Thank you, Steve. Now let's focus now on the objective of this project, which is basically, as indicated here, to determine the minimum number of spare engines and spare engine parts to support our flying schedule. All this, at the end, will be guided towards obtaining a tool for the end user in order to conduct easy calculations of that ownership. Right? But in order to obtain or to achieve this objective, let's take a look to the approach that we have taken in this project. Initially, we tried to obtain a closed-form development with that. As good engineers, as good scientists, we try to obtain a very nice formula that can explain everything and then capture and provide us that ownership calculation. However, this is a complex problem. It doesn't fit the classical inventory problem. It's a repairable inventory system where you have a closed loop, right? You have parts that are circulating. Some parts that are on the ownership sometimes are in service in the aircraft, sometimes are available in the inventory, or sometimes are in repair. So it's a much more complex problem. In addition to that, you have multiple sources of variability. Variability in the demand, variability in the repair times, different repair probability for the parts, for example. So that's something that increases the complexity. We also were facing the possibility of having a more general demand distributions for the problem, right? So we want to have an approach that was able to model that situation as well. But the mathematical and analytical approach has the limitations. We were able to obtain some basic formulations for that, assuming very specific conditions, for example, infinite capacity, under very specific also distributions for demand and repair time. And that's a paper that is coming that could be submitted soon. But we have limitations that we're not able to obtain in a mathematical formulation. That led us, therefore, to obtain or use a simulation approach in order to address the problem. By using simulation approach, we were able, therefore, to model all those processes that Steve just described in the different animations that we have, each of them in a logical, sequential way that model in detail the process and the complexity that we have. So we have that flexibility right there. From there, therefore, we were able to obtain simulation realizations of how that spare level changes in time. From there, we were able, therefore, to obtain some estimation what the ownership should be in order to obtain certain performance in our system. Therefore, flexibility in order to model those complex details of our process, such as borrowing of parts, scrapping, capacity constraints, harvesting processes, was one of the appealing approaches or features of that approach. Therefore, we can use a wide variety of distributions for modeling and capture the variability of our process. That's an important aspect of simulation. And also, it provides a possibility to understand the interrelationship between the repair of the parts in the shops and also how that affects the spare engine ownership. So that's very important in order for planning and for decision supporting our operation. In addition to that, the model also provides us a possibility to model the performance in a different way, which is more natural for our operation, in this case, out-of-service events. So we can generate from our model what is the expected amount of events in a given time of period, what is the duration that we expect for those events. So that's very, very useful for our field operations. Also, simulation provides us the possibility to run what-if analysis. We can conduct different simulations with different scenarios. Therefore, that opens a whole spectrum of possibilities for planning and for designing strategies. With this approach, with the simulation approach, we obtain two models. One at the higher level, which is the spare engine model, and one at the lower level, which simulates or models that repair of the spare engine parts, which is the shop pull model. Let's take a closer look to each of these models, starting with the engine spare model. In the engine spare model, we assume first that the repair is centralized. So we have a repair base where all the spare engines arrive for repair under different programs. Our available inventory can be in two ways. It can be either centralized in one location, or can be also distributed. So we can model both cases. One or the other can be useful depending on the type of engine. For example, there are some engines that are more reliable. We can properly reroute those aircraft in order to send those aircraft to a specific location. So in that case, centralized approach is more appropriate. But in other cases, we have other aircraft or other type of engines for which the repair and the removal of the engine has to be conducted on the spot. So in that case, the distributed approach is more appropriate. So a multi-location case is conducted in this case. So from the different processes that we have illustrated in the previous simulation, we can obtain a flow diagram, a flow of the process that we have, and this is the roadmap for our simulation. So based on that, modeling the engine removal, the replacement, the harvesting process that we can have, the repair time, the capacity that we can face in the process, then we have the roadmap for our simulation. Some key parameters that we consider in this simulation modeling is repair time. We have demand. Demand is, which is obtained from other sophisticated forecasting models that we have, where we can obtain what is the expected volume of repairs that we can have in a given period of time. We can have also capacity constraints, so how many heavy repairs we can have in the shops, for example. Also, specifications about the harvesting schedule, if necessary. In addition to that, this model can, therefore, as I mentioned before, can be extended to a multi-location setting, where you have multiple stations from which you can receive the removals, then being transported to the repair base. Then after the repair, those engines are coming back to those stations. For that, we also include in the multi-location case the possibility of modeling dispatching rules, from which we can select, based on different type of priority, which station is going to receive the next spare that is being completed at the repair. As usual, simulation, in our case, is run with multiple replications. Thousands of simulation samples are used in this case in order to generate the variation of the spare level in time, from which we obtain, therefore, an estimation of the ownership. In terms of performance, what we use here is 2 points of view. We have the traditional service level point of view, in which is obtained as a ratio from the demand that was successfully satisfied to the total number of requests. That gives us a kind of probability of availability of a spare engine or a spare part when it's needed. In addition to that, this can be used as an input for our model, in terms of that the user can indicate that he wants to know, for example, what is the ownership that I need to have for having a, for example, 95% service level. So that can serve as an input. In the other way, we can also use our model to set a specific allocation of inventory and then project what will be the service level under that allocation. So it's useful in that sense as well. From the simulation output point of view, what we have is basically different realizations of the spare level. For example, in this case, the engine spares. We have a transitory phase of the process, a warm-up period, and also we have a steady state, which is the part of the process or a part of the time that we want to focus on our process. From the point of view of calculating the ownership, we use a simple but elegant approach here, which is the following. We start in our simulation with a high initial ownership, such as that in the steady state, those realizations never reach the 0 point. Then, in the steady state, we provide a calculation of the percentile, or a given percentile of those realizations. For example, a 10 percentile will give us, therefore, an estimation of the 90% service level. So it's a simple approach that can allow us, therefore, obtain those ownership requirements at a given service level. The other point of view here is out-of-service events. When you have an aircraft that is out of service, we want to try to measure from our model what is the amount of events that we can have in a given period of time. For example, in a year, how many expected events you will see or expect to see. And also, what is the expected duration of those events? So that's very useful information for field operations. And it's information that the user can relate more than the regular point of view of the service level. Now, let's talk about that lower level of modeling here, which is the shop pull, in which case we are, again, modeling those different steps that Steve mentioned, all the way from the arrival, the decision of repair or not a given component. Do we have to scrap that component or, for example, conduct some purchasing of a new part? Or can we borrow that part from a upstream engine that is being introduced? In those cases, at the end of those processes, we always add those parts to the shop pool. But when it's time to rebuild the engine, we have to wait some time and therefore take those parts from the shop pool. So that's when you have this variation of going down in the shop pool or going up in the shop pool. So it's a closed loop system. Key parameters to mention here is that goal that we mentioned before, which is the time that we have to wait from introduction until starting the rebuilding of the engine. is very important. Repair probabilities, which are based on history of the repairs that we have. Scrap rates, capacity constraints. In this case, as in the case of the spare engines, the output of our model is corresponding to the variation of that spare level in time, from which we can obtain, therefore, the ownership requirements. And very important here is also, as Steve mentioned, engines are built with hundreds of parts. In our case, for the shop pool model, we run this simulation model for each of those individual parts. So each individual part has a parameterization of the repair times, repair probabilities, scrap rates, etc. In terms of how we implemented this solution for the end user, let's talk about the calculation tools that we have implemented. This calculation tool has two sides, one user side and then have an external server side. On the user side, you have a user interface, a graphical user interface, what has been implemented in Microsoft Excel, Visual Basic. And also there is a component, which is the simulation model. In this case, we have a executable independent program in Java that, for example, executes the simulation for the shop pool. Okay? And that was very important approach because the end user doesn't have licenses for third-party software, like Arena or Simio, etc. So we have to give a final solution for them, easy to use, and also very fast to run, for example, a case of 300 plus parts in the shop pool. So that was a very good option and a very good development. On the external side, we have the server side of the process of the implementation where we have the transactions data. We have an important warehouse of data here, Teradata type of the warehouse, from which we can obtain all the history of the repairs, and from which, conducting the proper processing of that information using a SAS program, we can send back to the user interface all the parameters that are required to run our simulation. Here I have some views of the tools that we have implemented. This is one of the menus for the shop pool calculator, in which the user can set up some of the important parameters, for example, which period of history they want to use in order to extract those parameters, so that's very important. We have other views of the tools here, for example, the main window for the different components that are being computed in terms of the shop pool requirements. So these are parts of engines, and you have different service levels. So our tool can compute those requirements for ownership. We have also the case of the spare engine calculator that works more as a what-if type of tool, when you can have multiple scenarios. Each row corresponds to a different scenario where you can parameterize with different values for that repair time, for different repair programs. You can set up different constraints in capacity, different service levels, so you can have different what-if scenarios to compare. In general, we have implemented these tools for 4 different types of engines, as indicated here. And an important component has been the automation. We have had the possibility to link the data warehouse, processing that information, send back that information as in a way of parameters. That helps a lot the end user in terms of running these calculations. Let's now take a look to several case studies in which we have utilized our tools. Let me take a couple before I get myself in out of service. So in the first case study, we're going to evaluate what is the impact of reducing the turnaround time in the repair in terms of spare engines ownership, and also what is the impact later in terms of shop pool. Let's start first with a little animation about what happened with the spare ownership in terms of engines. Let's assume first that the repair of our engines take 3 days in this case. So any time that an aircraft arrives, you will need 1 spare available in your inventory in this case. So these 3 engines will require, these 3 aircraft will require 3 engines in your spare inventory here. By the 4 aircraft that arrives, assuming that everything goes fine, we can reuse the engine that has been repaired from the first removal. And there, subsequently, we can do the same with the others. So at the end, you only need 3 spares in that case. But now assume that you have a longer time. You have 5 days now. So in that case, you will have to increase your your inventory of spare in order to cover the operation. It's not until the sixth aircraft, the sixth removal, when you can start reusing the previous removal that had been repaired, and then continue with the rest of the operation. So what happens is slow repairs demands larger inventory, in this case, in spares. That's exactly what happened with one of the business units, a production control unit in Tulsa. They came to us and asked, what is the impact if we have to reduce our turnaround time? This is what happened. This is the output from our model in which we obtain the spare ownership, as shown here in the blue bars, for different turnaround times. And in the red line, we have the current ownership, and this is a calculations at the 99% service level for the spare ownership. At the time of this analysis, the operation was conducting the repair around 84 days for each of the engines. So the model, the first thing that we were able to detect is for a 99% service level at the current level of ownership, we were not able to keep to that performance. So the question was, okay, in order to keep that same level of spares, not going to buy a new spare, we have to reduce about 20 days from 84 to 64. So we can keep the same current ownership, and therefore we need to reduce our engine repair time. But that has an impact in a different part of the process, which is the repair process, the shop pull. Let's try to take a look to what happened in that sense, with a little illustration, little animation here. Our engines arrive, different components are therefore disassembled for repair. Each component can have a different time for repair, right? So assuming that all the parts are repaired around this point, TAT, or turnaround time, then we can reassemble all the components and build the engine, and everything will be fine. But what happens if we want to reduce that turnaround time? Some of the parts won't be completed by that time. For example, this is a red block here. So therefore, we need some inventory in order to cover that and reduce our goal for the engine repair time and continue. But if we want to reduce even more, we're going to require additional inventory. So in this case, the impact of reducing the turnaround time is basically an increase in inventory, which is reflected for an increased investment also on the shop pull. That is exactly what we have in this chart. Going from the 84 days of the performance in our operation to the 64, therefore, represent an increase in the investment that we require for those shop pull parts. Of course, there is a trade-off. You can decide buying a spare in order to have higher service level, or buy more parts. In these particular scenarios, in these particular cases, the best decision was to buy more parts and improve other parts of the process in order to reduce that turnaround time. So that case is very interesting because it gives us, therefore, the interrelationship between spares and also the impact in the shop pull in cases when you need to reduce the turnaround time. The second case is related to how we manage the spare engines in the field, in different stations. Now, in this case, we assume that we have a distributed inventory in which we can have the possibility of borrowing spares between those stations. And we want to see what is the impact of reducing the duration of our service events. So let's start with the chart in the condition in which we don't have borrowing. We don't have borrowing between the stations. In this type of operation, that happens is that each station have their own inventory, but as soon as they use the last spare, they have to wait in order to receive the next one in terms to continue the operation and eliminate the problem of the OTS. But instead of that, we can also have the possibility of borrowing spares from other inventory available in the system. So that's what happens in this second chart that we're showing here in these red bars. When we allow to, instead of waiting for that spare to arrive to the repair base, we can look to the opportunity of having one available spare from other station and move it quickly to that station requiring that spare, and then mitigating in a big way the impact of the out-of-service aircraft. For example, the case of Station 2, which is representing one of our major hubs. And you can see that the impact of the OTS is different in different stations because of situations of distance or situations of demand, for example. So in this case, in station 2, which is the one that was resulting with more impact with no borrowing, we're able to reduce in an important manner the impact of those out-of-service events. So that's important in order to define strategies, define rates, and how we can properly borrow those spares in the system. Let's talk to complete our presentation about the impact that this has happened in our company. First, we have a better planning of our spare ownership. Has been a big achievement to include these analytical tools in the TechOps organization, which is not the highest analytical organization in our company, so that's very important. Compared to previous methodologies, which were more manual methodologies, we have obtained the possibility to have important savings in inventory. We have also the possibility now to adjust better our inventory as we retire fleets, and we also increasing other fleets in the system. Savings can be in the range of millions, 7 millions, for example, for one of the fleet or the type of engines, between 15 and 27% in shop pool parts. And our application is currently patent pending. Just to conclude, simulation is the preferred approach because of the complexity that we have found in this process, and we want to represent and capture the availability of the process. This also provides us the necessary accuracy in order to model the situation of the calculation of this ownership in a more accurate way. And also provide us this important way to relation the shop pool with the spare engine ownership, which is very important. Also the possibility to measure the performance in a more natural way in terms of out-of-service aircraft, which is very important for field operations. In addition to that, that opened the door to apply this model to many other type of key assets in the company that also have a type of repairable inventory system, like auxiliary power units. Finally, I just want to mention acknowledgement for many people in the company that have helped in one or other way in the implementation of this project. And also thanks to the organization of this award and the judges for taking the time of reviewing our work. We really appreciate it. Thank you very much.